Um, Hello guys once again, right? I hope that you are doing okay, right? So we're going to look at some revision on probability, and I'm focusing strictly on grade 12 probability, which is counting principle. Ne? I think as time goes on, we shall have grade 10 and 11 probability revision too, right? But for today, I want us to just tackle questions on counting principle. um, Probability is not really difficult, um, especially counting principle, right? This is where we should get our marks most of the times. Okay, so we have 9 cars of different of different makes, right? Of which 4 are black, uh, and of which 4 are black, are to be parked in a straight line. Hey, their English is not very much Englishing nicely then. But then here we have 9 different cars, right? Of which 4 are black. Yo, these people. Okay, it's fine. So 11.2.1. In how many ways can those cars be parked? Since there are 9 good people, right? We are talking about arrangements, right? And since it's 9, definitely we shall say 9 factorial, right? 9 factorial ways. So 9 factorial ways gives you what? To give you 362 880 ways, in which you can park those. Why are we saying 9 factorial? Let's remember that you want to park them in a straight line, and then it's 9 cars, right? So it will be the first position, second, third, fourth, fifth, sixth, seventh, eighth, ninth. So for the first position, you have 9 options from the 9 cars, right? So you can say 9. If one of the cars you chose it to be here, it means for the second position now you have 8 options. And then if 2 of them now are occupying the first 2 positions, now you're just left with 7 options from the remaining ones. And then it goes on like that, right? It goes on like that. Put multiplying between there. Now, good people, let's understand that if you have 9 multiplied, like 9 multiplied by decreasing numbers like this until 1, we can easily call that 9 factorial. If you have 4 multiplied by 3 multiplied by 2 multiplied by 1, you just say this is 4 factorial. 3 multiplied by 2 multiplied by 1, you can just say 3 factorial. You can go to your calculator there is that factorial there. So that is factorial notation. Right, and then 11.2.2, I think that is where the juicy matters are. 11.2.2 then says, if the 4 black cars must be parked next to each other, determine in how many different ways can the cars can be parked. Hey, they're English. All right. 4 black cars must be parked next to each other, right? They must be parked next to each other. So I always say that that is a restriction there. Let's say again we have 9 options. I get 1, 2, 3, 4, 5, 6, 7, 8, 9. So from those cars, right, we're going to say 1, 2, 3, 4. We're gonna group them, right? These are the 4 cars that must be parked next to each other. But inside there, right? Since it's 4 of them, these are the 4 cars inside here that must be parked next to each other. One of them can be here. So for the first option or position, I have 4 options, right? For the second position, I have how many options? If one of them is now sitting here, it means now 3 of them are left. I can choose to sit here. And then now 2 of them will be left, and then 1. Right. So this is what is happening inside the box. That is what is happening inside the box. Now the remaining ones, right? The remaining ones will be 1, 2, 3, 4, 5. Those are the spaces that are left. And there are 5. However, I always say to people, right? After grouping them, these ones, ne, I want you to take that box as the fifth position, meaning to say that you now have 1, 2, 3, 4, 5, 6 positions that are left. Okay, so it means that now so it means that the total, or rather the final answer, good people, right, the final answer should be the restriction. I always say, you write how many do I have in the restriction, right? In the restriction we have how many? We have 4. And then you say for the remaining ones, right, for the remaining ones it will be how many spaces? It is 5 spaces, but now you're going to add 1 for this group, ne? You add 1 to say the remaining ones, you have 6 spaces. So the final answer would simply be 4 factorial multiplied by 6 factorial. So it will give you the number of ways that they can be packed. Did anyone get this? Hey, nice. Is that a question or you got it? Okay, sorry, I'm not able to see. Let me check. Okay, nice. All right, so that is how we solve it, good people, ne? For probability in terms of counting principle, you look at the restriction, those that they want next to each other, you group them, right? And then you say, in this group now, how can I place them? And then you see there, for the first one I can choose one of the 4, one of the 3, one of the 2, and then the last one will be here. And then after that, this now you take it as one thing, right? To say now the total possibilities outside. So oh yes, we usually call it like this, right? Sometimes, good people, I invent very good strategies, and then those strategies you might find that I forget to mention them. So easily what you can do, ne? You can say all the time on probability questions, you just say inside, ne? In terms of inside, this is how many are in the group. Inside they are 4, right? And then you write outside, ne? Outside you're going to say it's 1, 2, 3, 4, 5, and then you count also this as 1, right? To say you have 6 outside. Then from there you just put factorial, you get your answer. Okay, so you multiply them and then you get your answer. Right, let's look at the next one. Yeah, we got some nice one also here, and then maybe due to time I might have to just do it for you guys, then maybe you can try the next one. So we have a 4-digit code here, right, which is required to open a combination lock, and then the code must be even numbered and may not contain the digits 0 or 1. Digits may not be repeated. 10.2.1. How many possible 4-digit combinations are there to open the lock? Hey, very nice stuff, good people. The 4-digit code, ne? So we say already how many spaces? We're going to have 4 spaces. Then now, from those 4 spaces, right? From those 4 spaces, we shall then say, okay, for the first one, remember the code, the restriction says that the code must be even numbered. The even numbers that we have is what? It's 0 is even an even number, right? 0, 2, 4, 6, 8. Right. But they said they may not contain 0, so we're gonna remove that. So we have 2, 4, 6, 8, right? Right. They must be even numbered. So let's understand one thing, good people. These are the even numbers that we have. Ne? These are even numbers. However, when we say something must be even numbered, ne? Let's understand this word properly. When we say something must be even numbered, this means that that number must end with either 2, 4, 6, 8, or 0. But we said because it must not contain 0, we remove it. For example, 22, is it an even number or not? It is an even number. Okay? Why do we say it's an even number? Because it ends with a 2. What about 576? Is it an even number or not? It's an even number, right? Because it ends with a 6. What about 10,333? 10,333. Is it an even or an odd number? Now this one is an odd number, good people. Why is it an odd number? Because it ends with a 3. It must end with either a 2, 4, 6, or 8 for it to be considered an even number, no matter how ugly it is. For example, 55580761543112118. Is it an even number or not? You don't look at the numbers, just look at the last one. Because it ends with an 8, it's an even number. You understand me? So that is what the word even numbered means. It means your code here must be even numbered, which means here you must have either a 2, or you must have a what? Or you must have a 4, or you must have a 6, or you must have a 8. So how many options do you have for the last part? You have 4 options, right? You can choose either one of these. However, for these other ones, good people, there is no restriction. Ne? The only restriction is that now the digits may not contain 0 or 1. So let's see the total number system that we have, right? In terms of how we can construct this, we can have where 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Ne? Now, for the first one, we already know that 0 was excluded and even 1 was excluded. I get that's what they said there. They said we must exclude those. Now, for this first one here, ne, how many options do I have? Right? I can choose 2 to be there, or I can choose 3 to be there, or 4, or 5, or 6, or 7, or 8, or 9. So how many options do I have? 1, 2, 3, 4, 5, 6, 7, 8. Ne? But would it be correct to put 8 there? Can someone maybe try? Is it correct to put 8 there? To say yes, we have 8 options. It could be 2, 3, 4, 5, 6, 7, 8, or 9 there on the first position. Going once. Going twice.
It's not correct, sir.
It's not. Why is it not correct?
Because they said digits may not be repeated.
Perfect. Because they said that the digits may not be repeated. Understand this. From these 4 options, you might find that there is actually, you might find that there is 2 here. Now, if you put 2 again here, since you said that you have 8 options, right? If you put 2 again there, then it means you are repeating 2, and that is not allowed. So because of that, good people, the only options that we have, since 1 is already chosen from these, right? So we have 7 options left. Then from there, we'll have 6 options, we'll have 5 options. So it goes down like that. Great. Because why 6 options here? And we said 7 options. It means now we have already chosen 2 numbers. So if you chose 2 numbers, it means you have 1, 2, 3, 4, 5, 6 options, right? It might not necessarily be 2 and 3, it can be any of the combinations, right? So you have 6 left and then 5. Good people, that is what you do, and then you get your answer there. So how many possible 4-digit combinations are there? You put that in your calculator. I think you should get something like 840 combinations. 840 combinations. Great stuff there. Beautiful stuff. Right. And then we go to 10.2.2. Let me see if I'm able to perhaps erase these parts here that we already worked on. So for 10.2.2, it says calculate the probability that you will open the lock at the first attempt if it is given that the code is greater than 5,000. And the third digit is 2, right? Very, very interesting question there. Very interesting. So what does it actually say? Calculate the probability that you are going to open that lock at the first attempt. If it is given that the code is greater than 5,000, right? The code is greater than 5,000 and the third digit is 2. So these are restrictions there. The code is greater than 5,000 and the third digit is 2. Those are restrictions there. So, how can let's see, how can we say something is greater than 5,000, right? How can we see that this thing is greater than 5,000? And they want the probability, right? So yes, we can get the number of maybe the number of ways first, right? And then from there we can calculate the probability. Right. Quite an interesting question, right? Let's understand the following, good people. A number that will be greater than 5,000, ne? Let's see. Do we agree that if your code is starting with a 2, ne? Let's say your code is starting with a 2 and then it has 2 and then other numbers here, ne? Oh, sorry. Do we agree that this code is going to be less than 5,000? Right. If your code starts with a 3, do we agree that your code would be less than 5,000? Right. If your code starts with a 4, do we agree that it will be less than 5,000? Because at the end of the day, good people, let's understand that when you make the code, you're actually making a number, a 4-digit number. You understand me? Just like your password there, if your password is 8001, it's actually a number. So, and 8001 is greater than 5,000. So they're telling you that the code number 1 must be greater than 5,000. And the only way, good people, for it to be greater than 5,000, that is if it starts with a 5 or a 6 or a 7 or a 8 or a 9. You understand me? That is only when the code is going to be greater than 5,000. It either starts with a 5, a 6, a 7, 8, or it starts with a 9. Right. So let's see. If it starts with a 5, right? So let's see. Let's check. 5. Okay, let me maybe write it here, ne? So let's go through it step by step, right? So let's say our code, so it means we'll have 3 options. So this is our code here. We shall have 3 options, right? Remember, it could start with a 5, a 6, or a 7. All right, which means we can say we have 3 options, and then maybe for these 2 we can treat them separate, right? To say so let me write here 5 or 6 or 7, right? It's 3 options. So we'll say, okay, we can start there with a 5, a 6, or a 7. Ne? We're dealing with the first 3 to say you can start with a 5, a 6, or a 7. Then if it does that, right, remember we're told that the last digit must be 2. It means for the third digit, 1, 2, 3. It means here we have only one option there to say it must be 2 here. Ne? It must be 2. Now how many options will we have if it's like that? Here we said it could be 5, 6, or 7. It means for the next one, for this position here, I could choose what? Remember this one is already gone, right? So we could choose 1, 2, 3, or 4. Ne? Do you agree that there we have actually 4 options? Let's see. Let me see something here. 1, 2, 3, 4, 5, 6, 7. Okay, and then here we can have, if it's one of those, right, it could be 5, a 6, or a 7, right? So it means that, let me write it properly, good people. Let me not confuse you. This probability is something else, but then it's nice. So what I'm saying is that you have 1, 2, 3, 4, right? And then the third digit must be a 2. For sure here you must put a 2. However, for this space here, right, for it to be greater than 5,000, right, you could choose it. You could start with a 6, a 7, or an 8. And or you could say from 5, 6, 7, or 8, right? So you can say, okay, I could start here with 5. So you can say let me write them here. So the 2, we're not going to include it. We say 3. Okay, 2, 3, and 4 we don't include, right? Then we have 5, 6, 7, 8, or 9, right? You have those options there. Now, okay, for the second one, that's where the 3 and 4 is going to come into play. But for this one, for this first position, right, you could say I start with a 5, a 6, or a 7. You could start with these 2 first, and then you can maybe end with the rest. Or put it simply, just say maybe one of the 4, right? So it means here you have 4 options. But is it 4? Sorry, it's 5 options. Yeah, it's 5 options. Right, so you could say a 5, a 6, a 7, a 8, or a 9, right? You have 5 options there. And then for the second one, how many options will you have? Well, because you chose 1 there, and then already 2 is gone, then you have how many options? 1, 2, 3, 4, 5, 6. So now you have 6 options, right? And then when you remove that one, it means you will have 5 options left, right? So this is for the first part of the question. This is for the first part of the question. You can choose either of the 5 there. But you are not done. You understand me? You are not done because one can say that from the 5 options, you could have started with 5, you could have started with 6, 7, 8, or 9. However, I'm thinking. However, the problem with this approach is that how do we know that on this 5 here there is no 4? Because remember we included 4 here, ne? However, how do we know that we didn't start with the 4 there? What makes us sure that from those 5 options there is no 4? Right. Then it becomes a bit interesting, right? Because from the 5 options, yes, it could be 5, 6, 7, 8, or 9, but it doesn't also restrict it starting with the 4. So because of that, you must do it manually, good people. What do I mean manually? You're going to say, okay, you're going to start by saying, okay, for this first option, I know for sure, I'm going to be choosing 5. And then for this one, for sure, it's going to be 1. It's going to be 2. Ne? Then you do it again, saying for sure, I know here it is 6. And then here we know it's 2. You continue doing that for the rest of them, right? You continue doing that for the rest of them, right? Like this. And then after that, you're going to add, because you are saying it could be like this, or it could be like this, or it could be like this, or like this. Now, in probability, the moment you use the word or, that means that you are adding. So you're going to add all those probabilities there. Right. Yes, you can ask, ma'am.
Sir, why did we put 1 for the first position?
That one there stands for the 5. And then this one here stands for the 2. Here it stands for the 6. And then this one stands for the 2. And then here it stands for the 7, eh? And then here it stands for 2. And then here it stands for 8. And then here is a 2. In fact, we are missing 1. You see, we are also missing you starting with a 9. Again. Yeah, starting with the 9. So you say 1, 2, 3, 4, starting with the 9. Let me just put it here. So to say 1, 1. Here it's a 2, and then here is a 9. Right. Those numbers there, any number that will start with the 5 is going to be greater than 5,000. It means you have met the restriction. And then any number that will start with a 6, it will be greater than 5,000. Start with a 7, it will be greater than 5,000. Start with an 8, it will be greater than 5,000. Then if it starts with a 9, it's going to be greater than 5,000. While making sure that the third digit is always 2222. Yes.
Sir, so for the first row, the 5 that you put there as your first position, not for the number of positions, it's for you saying that you just randomly choose 5 there.
The number I put here.
Yes, sir, that 5 near the 6.
That 5 was to say I could start with a 5, a 6, a 7, a 8, or a 9. You see?
Oh, okay, sir. Yes, sir.
Yes, but the problem with that method was to say, since we also have 4 there, we have 3. Ne? The problem is that when you put 5 here, how sure are we that from these 5 options, it's exactly 5, 6, 7, 8, or 9? How sure are we that there's no 3 or 4 there? You understand me? And once there's a 3 or 4, is that number going to be greater than 5,000? It's not. You see? So that's what you must always face, especially for problems that we're going to talk about, smaller than or greater than. That is what you must always try to look out for. Okay? Is that okay? Right. And then now, another thing we need to consider is the first restriction that we were given. We were told that the last number must be an even number, isn't it? Now, let's understand the following. Since here, we already have 2 as an even number, the only even numbers that we'll be left with, right, it would be 4, 6, and 8. So it means that for the last one here, you would have 3 options that are left, right? You can put any one of those there, right? 4, 6, or 8. So that means from those 3, you just have 3 options there. You can choose any one of those. Ne? And then, right, so I don't like that I have these numbers all crossed out and stuff here. Let me just write it properly here. 4, 5, 6, 7, 8, and 9. Now we said 2 is already crashed out, right? We already know that there must be a 2 there, but we also crash out 5 because we know that there must be 5 there, right? However, for the remaining ones, how many options do you have? You have 1, 2, 3, 4, 5, 6, right? You have 6 options. However, let's check here. In terms of here, we could put either 6, we could put 4, or we could put 8. So we have 3 options, right? So let's just say we put 6. It will mean that how many options do we have left? 1, 2, 3, 4, 5. It means you're going to have 5 options left. So this will be your first one. See, that will be your first one there. You must start understanding it from here. If you can get it from here, then trust me, for the rest of them, it will be okay. What I need to caution you, especially when you do a counting principle, make sure that you do not think of this number as a number in here. Because these 3 and these 3 are not the same, good people. If you can get it from there, you are okay. These 3 and that 3 are not the same. This 3 here says I have 3 options I can choose from. You understand me? Where are those options coming from? Let's remove. Where are those options coming from? They are coming from your sample space, right? They are coming from your options here. This is called your sample space. Now, in your sample space, you already know that here should be 5. That is why we have 1 here, to say you have only 1 option there. We know that here should be 2. That is why we have 1 here, to say you have 1 option left. When you do that, you are crashing out numbers in the sample space, reducing your sample space. Now your sample space has how many options? 1, 2, 3, 4, 5, 6. You have 6 options. I get it. Now, here on 3, you are saying I could choose either 6 to be here, or I can choose 8 to be here, or I can choose 4, so that the number becomes even numbered, like the whole code becomes even numbered. So you have 3 options there. The 3 there will stand for those 3 options. But from the 3 options, you're going to take only 1. That is why when you come back to your sample space, you must crash only 1. Either 6, or you crash 4, or you crash 8. You understand me? You must crash only 1. So hence I'm saying, let's say you crashed 4. How many options do you have left? You have 1, 2, 3, 4, 5. You have 5 options left. Are we clear? That is what is happening there. Then you go further and say, okay, you are done with the first one. Right, and then you go to the second one. Remember the second one, this original sample space was 2, 3, 4, 5, 6, 7, 8, 9. I get it. Now, we know that for sure, it must be a 2 here. So we must crash 2. For sure, it must be a 6 here. So we must crash 6. And then what do we say? Remember here, it must be an even number. So from those that are left, how many even numbers do you have left? You have 4, you have 8, right? So you have only 2 options. That is the 2 you write here. It means you can put 4 here, or you can put what? You can put 8. Then how many options would you have left? So let me just say I'll crash 4. How many options do I have left? I have 1, 2, 3, 4, 5. So I'll put 5 here and then say multiply. Perfect. I hope it's coming along. And then perfect. Good people, we are getting it. We are getting there. Then we go further and then say the next one. 2, 3, 4, 5, 6, 7, 8, 9. I know it's long. It's 5 marks, by the way, good people. It means you must work and think a bit harder, right? Now, the same thing here, right, would happen. You crash 2, you crash 7. Then from here, right, the even numbers, you can either choose 8, 6 or 4. It means you have 3 options there. Then you're going to crash at least 1, and then you'll be left with 1, 2, 3, 4, 5. You're left with 5 options, and then you have that. Then second last. Okay, you have 2, 3, 4, 5, 6, 7, 8. There is your sample space. You crash 2, and then remember you must start with 8. You crash 8, and then you say now from the even numbers, right, you are left with 4 or 6, which means 2, right? And then you crash maybe 6, and then you are left with 1, 2, 3, 4, 5. So you have 5 here, good people, right? And then after that, last one, right, 2, 3, 4, 5, 6, 7, 8, 9. So same thing here. You're going to crash 2, then you crash what? 9, right? And then you say from these even numbers, I can choose 4, I can choose 6, or I can choose 8, right? So you have how many options? You have 3 options, and then from there you crash one of them. Maybe I crash 8, then you're left with 1, 2, 3, 4, 5 options there, good people. Then you take your calculator and then you add all of them and say the total number of ways. Total number of ways will be how much, right? So can you maybe put for me in a calculator there? You shall say maybe 1 times 5 times 1 again, then times 3, you get 15. So that would be 15 plus what? 1 times 5 times 1 times 2 is 10, right? You say plus 10, and then 1 times 5 times 1 times 3 is 15 again, plus 1 times 5 times 1 times 2, that is 10 again, and then lastly 15. So what does that give you? 15 plus 10 plus 15 plus 10 plus 15. So you'll get 65, right? Isn't it? Then from there you say, therefore, remember probability, right? Probability is equal to the number. Probability of an event is equal to the number of outcomes in the event over the number of outcomes in the sample space. The number of outcomes in the event, we got it to be 65. And then those that are in the sample space is when we didn't have the restrictions, right? When we could just make our code that they said it must not have 0 and 1. So meaning that your sample space is in 10.2.1, which is 840. And then you get your answer. Right. Wow, I'm glad that we actually killed it, good people. If you can check the memo, right, go and check. You can write senior certificate. It's what? No, it was asked. This question, good people, was asked November. So just go and check, ne? It was asked November. November what? 2022, ne? November 2022, paper 1. Those that wrote in 2022, 2022 was interesting. So just go check to November 2022, paper 1. In fact, I'm going to do the courtesy of sending you that paper in the group, right? And check the memo there. You will see that in the memo, they solved it quite differently. However, I would advise that maybe you attempt it in a way that you will understand, to say, because what we did here, I believe it's a procedure you can always apply everywhere, right? To say, I need my digit to be greater than 5,000. So I can start with a 5, a 6, a 7, a 8, or 9. But making sure that the third number is always what? The third number is always 2. Then from the sample space, you are just crashing. right? I call it Candy Crush, right? And then when you are crushing there, right, you then say, oh, now for the last one, let's remember it must be an even number, so I can choose one of those. So I must crush one of those in my sample space, and then from there I just look at the remaining outcomes, the remaining options, and then I put them there. Good people, it's much understandable that way. Remembering that that 2 doesn't mean that it must be a 2 there. It means it could be either 4 or 8. So you must go and crash that in the sample space. Then you'll be okay. Is that okay, good people? Any question? Right. No, if there is no question, good people, just go try and digest this one, right? I'll even send it on YouTube, right? So that you can, go back to it, try and crush it more, and then you'll be okay, right?